Unit 8 solutions. It is time for a review sheet so that you can do well on a test. Here we are looking at questions 1 through 4. Can you use those solubility rules that we've been talking about and using in this unit to decide if these things are going to be soluble or insoluble? Starting first of all with titanium hydroxide. And you probably remember the song and that famous verse, hydroxides in general don't dissolve at all. Of course, there are some exceptions to that, but in this case, this stuff is insoluble. It does not dissolve. And neither does this one. Or you might look at the rule about chlorides and see that most chlorides are soluble, but don't forget to look at those exceptions and see that silver chloride is not soluble. Now let's look at this one a little bit carefully. Of course, the rule for chlorates that you have is that all chlorates are soluble, but don't forget this rule as well that tells us this is soluble. What group of elements is this from? The alkali metals. That's right. And remember, alkali metals and ammonium salts, whatever they may be, can always be depended on for solubility. Almost kept singing there. That was so much fun. So let's look here at this next problem about net ionic equations. And we have 4 examples here to look at. We have 4 examples here to look at. We have 4 examples here to look at. We have sodium sulfide. We have lead chlorate, lead 2 chlorate. So we have to have 2 chlorates because the lead has a charge of +2. What's the net ionic equation? Well, to decide what is going to happen here, we're going to look at the cation from this compound and the anion from this compound and decide if we put those together, will we get a reaction? And the answer is no, because alkali metals are soluble and chlorates are soluble. Now, let's look at, oh, that's so dark we can't hardly see it. Let's undo that and find a different color. Let's look at this cation and this anion, lead and sulfur. And let's look at the rule. And there's a rule about sulfide. It says sulfides are not generally soluble unless they're with an alkali metal or ammonium. So the product, lead sulfide, is going to be insoluble. It's going to form a precipitate. So we're going to show that part of the reaction just by showing the ions that make up the lead sulfide. The lead that came from the lead chlorate and the sulfide that came from the sodium sulfide. And we're going to include the charges, and then we're going to show that they combine when they are in solution because they are not soluble and they're going to form a precipitate and settle to the bottom of the container. Now that, the highlighted equation here is what you need for the net ionic equation. Well, let's look at the next example. Silver 1 nitrate, remember the 1 is just telling us the charge, and so I'm going to kind of write that over here, AgNO3. That's in solution, and so those ions are actually separate and floating around. And sodium phosphate is also in solution because sodium is an alkali metal. So we have these ions. Let's check to see if we take silver and phosphate, will that form something that is not soluble? Yes, it does. It forms silver, Ag, which is +1, and phosphate, which is -3. So we have to have Ag3PO4. That is going to form. It's not going to be soluble. So let's show the formation of the silver phosphate. Ag, of course, has a charge of +1. And phosphate, your good old friend phosphate, has a charge of 3-. So we have the ions and the final product, but it is not balanced. And it's not balanced for two reasons. One reason it is not balanced is we have 3 silver and here and only 1 silver here. So the silver is not balanced. Also, if we look at the charges here are not balanced. And so to make this balanced, we need a 3 in front of the silver to give us both a charge of +3 and balance the charges to make them add to 0, and to make it so we have the same number of silver and phosphorus and oxygen on each side of the arrow. So the highlighted portion here that I'm highlighting right now is the net ionic equation for this reaction that's described. Let's go look at the next example. Potassium carbonate and calcium bromide. Well, let me write those over here. I'm going to do it write them in a different color this time. Potassium carbonate. Now, if you don't have these memorized, be sure you're using your equation sheet to look at the ions and their charges. Calcium bromide, CaBr2. Okay, let's look and see if we will get any precipitate. Well, I know that potassium and bromine, they are not going to form precipitate because potassium is an alkali metal. I don't even have to look at the bromide to see if it's going to make a precipitate. But let's look at calcium and carbonate. Oh, calcium carbonate is not soluble. Carbonates are insoluble, and it's lucky that it's so, or else our marble buildings would melt away like snow. Okay, so let's write the net ionic equation for this. We know that calcium, when it combines with carbonate, is going to form a precipitate. Calcium is +1, carbonate is -1. Calcium is +2, carbonate is -2. So this looks to be balanced and complete, and so this is the net ionic equation. Now, on the test that you will be taking, it is possible that you would encounter something like this, where if you look at the lithium and the carbonate, and you look at the ammonium and the hydroxide, and you think, am I going to get a precipitate when I combine this and this? No, because alkali metals and ammonium salts are not soluble. So either combination of these will not form a precipitate. And so this is making no reaction, and that's all you need to tell us for the net ionic equation. Number 6 and 7 ask this. They say we have we have this solution that must be prepared. Must be prepared from a solution that's this concentration. So I think I know how to do this problem. This looks like a problem that we're diluting something. And if we're making a dilution, we are going to use our friend molarity 1 times volume 1, come on, pen, volume 1 equals molarity 2 times volume 2. That's the problem, that's the equation we're going to use to solve this problem. Now, you are going to, of course, want to start listing the things you know. What are the things you know? You want to get this organized. You want to get M1 and V1 and M2 and V2 carefully identified. If you don't have them identified, you may not be able to work the problem correctly. Now, M1, if we're actually diluting something, M1 has to be the more concentrated. So that's going to be the 1.50 molar. And M2 is going to be less concentrated. That's the 0.0800 molar. Volume 2 is how much we're going to make, 2 liters or 2,000 milliliters. And I changed it to milliliters is I just noticed here that we want our answer to come out in milliliters. We want milliliters of V1. That's what we want. So that's our unknown. So let's substitute in our numbers now that we have into this equation. M1 is 1.50 molar. V1 is our unknown. M2 is 0.80 molar. And V2 is the size of our volumetric flask. And I'm using 2,000 milliliters so that I have the right unit when I come out. So if I solve this for V1, I'm going to have the right answer. Number 7 is similar. I'm going to start here by writing the things I know in this problem. But how do I tell what kind of problem I've got here? Well, the first key is this word stock solution. A stock solution is something we often start with and dilute to some concentration that we need to work with. So we have a stock solution, and what do we need? We need to make this. We need to make this. So, once again, this is going to be a problem where we know M1 and M2. Do you see which is which? M1 is the 10 molar, and M2 is the lower concentration, 0.375 molar. And what else do we know? We know the size of this container that we're going to be mixing it in. Remember, you used a 250 milliliter volumetric flasks for all the dilutions that you made, and that's what this person is going to be using too. 250 milliliters is our final volume. What we're looking for is how much of this 10 molar sodium hydroxide do we need to use to dilute. So I'm going to use the equation M1V1 equals M2V2, and M1 is the 10 molar. V1 is what we're looking for. M2 is what we're going to dilute to, 0.375 moles per liter. And our volume is 250 milliliters. Now, did I check here to see? It doesn't. Oh, yes. It doesn't specify what our volume needs to be in, so milliliters is going to work just fine. So we're going to, of course, solve this problem by dividing both sides of the equation by 10 moles per liter. 10 moles per liter. This cancels out, leaving us with V1 equals, and you're going to solve that and get the correct answer for the problem. And don't forget, the correct answer to the problem is to describe in a sentence how you would make this stuff. Well, you did this in lab. You know that you're going to take this 9.38 milliliters of 10 molar sodium hydroxide. You're going to put it into a volumetric flask, and you're going to add enough water to make 250 milliliters of solution. You're going to fill it up to the calibration line on the 250 milliliter of volumetric flask. Number 8 is a different kind of problem. In that we're not making a dilution. What's our known and unknown? That's the best thing to look at first. The things we know is that we have 18.0 molar H2SO4, and we know something about that we want to get 2.45 grams of this H2SO4, but we don't know how many milliliters that volume is. Well, this turns out to be a good example of why it is helpful to keep track of your units, because the units here will help you solve this problem. So what we are going to do is just kind of play with our units a little bit. I'm going to write down the 2.45 grams of sodium of sulfuric acid, H2SO4. And then somehow I need to get grams to change into volume. Well, I know that I've got this relationship here between moles and volume, so maybe I'm going to switch this from grams to moles. And I can do that pretty easily. 1 mole of H2SO4 is how many grams of H2SO4. I can get out my calculator or get out my periodic table and calculate this. It's 98.09. That's the mass of 2 hydrogens, 1 sulfur, and 4 oxygens. And what that has done is made these units cancel. So in my puzzle, I'm trying to come out with milliliters, but I have a relationship between moles, so that if I have moles and liters, I have this relationship right up here with 18 moles per liter, right? So that means 18.0 moles of H2SO4 for every 1 liter of solution. And if I really want my answer to come out now in, those units canceled, and I want my answer to come out in milliliters, so I'm going to have to get liters to cancel, and my last unit up here is milliliters. 1 liter is 1,000 milliliters, and I calculate that, and I have my answer. To continue watching this review, go to part 2 of this video series.